Hello everyone, welcome to the first lecture of week 7 in which we'll continue our discussion on transmission line models and the use of these models for understanding their performances under different operating conditions. We have at length talked about the different line models, the lossless behavior, surge impedance loading, and a bit about Ferranti effect, etc., etc. In today's discussion, we will specifically look at what is meant by reactive power compensation, why this compensation is actually needed. We have discussed about it in the previous lecture, where often the line is loaded at percentages beyond the surge impedance loading to ensure proper utilization and to have good transfer capacity, power capacity transfer from source to load. So usually the receiving end voltages would be lesser than the sending end voltages in the transmission line, and more is this voltage difference, more would be the corresponding active power loss in the transmission line, which we will see obviously when we jump into our next module, which is going to be on power flow analysis. The reason of maintaining or ensuring proper voltages or voltage profiles in the transmission line at different line lengths is just to make sure that the I square R loss or the active power loss is as low as possible, while ensuring majority of it power being transferred from the source ends to the load ends. And that's the reason why reactive power compensation is necessary, so that voltage profiles can be improved, and in a way the reactive power and voltages, they are a bit strongly coupled compared to the coupling between the phase angle difference across the line and the corresponding reactive power flow, which again for time being I would say we will discuss more when we discuss power flow analysis. So overall takeaway from this particular discussion or today's lecture would be that we need reactive power compensation to ensure proper voltage profiles in the transmission line when the lines are loaded beyond surge impedance loading. And we have discussed about surge impedance loading in the previous lecture and talked about complex power flow expressions, in which we have observed that for a transmission line with known A and B parameters and receiving end voltage phasor acting as a reference with sending end voltage leading the corresponding sort of having a phase angle difference delta with respect to receiving end voltage, the corresponding receiving end real power and reactive power, similarly the corresponding sending end real and reactive power, they have these expressions. And if we were to plot these expressions on a complex plane, which is a PQ plane, P on the active power, P on the x-axis and Q reactive power on the y-axis, then these indicate or represent circle for different values of delta. The points may be different on the different circle, but the circle is a perfect circle with center as minus A by B conjugate, A conjugate by B conjugate, VRL conjugate, with radius as VRL SL by B. VRL and VSL, they refer to the line to line receiving and sending end voltage, and similar expression also exists for the sending end expressions. These locuses, they are very similar to the locuses that we saw for synchronous generators, specifically capability curves, and these in a way help in assessing the performance characteristic of the given transmission line under different operating conditions, and that's the reason why the understanding behind these locuses is important. For a lossless long line, to be specific, by lossless long line we mean the corresponding per unit resistance is 0, the corresponding per unit conductance is 0, the corresponding per unit inductance and capacitance need not be 0, and specifically for surge impedance loading of a lossless long line, the surge impedance value itself is a pure resistor, the characteristic impedance is a pure resistor, and the phase angle beta is equal to 2 pi f into root over of LC, and capital or small ll is the line length. So if we substitute these expressions of lossless line or attributes of lossless line in the ABCD expressions, then what we see here is that A, which is usually supposed to be a complex number, for a lossless line, A turns out to be a pure scalar and B turns out to be a pure complex number. That means if we have to represent or find mod of A and the angle of this theta A with respect to receiving end voltage, then for lossless line, theta A is 0, mod of A is simply cos of beta LL. And similarly for B, which is mod of B at an angle theta B with respect to receiving end voltage, theta B is perfect 90 degrees or pi by 2 radians, and mod of B is ZC sine beta LL. So if we put in these specifications into the expressions of receiving end power, sending end power, real and reactive powers, we see something again specific or very beautiful or very similarity in the sense the expressions of real power, they closely match the expressions of a cylindrical pole synchronous generator on a per phase basis, whereas similar expressions which we saw for reactive power expression in a cylindrical pole synchronous generator, similar expressions also exist in reactive power at the receiving and sending end. And furthermore, the sending end and receiving end real powers, their expressions are perfectly identical. The values are perfectly identical, and one would wonder why. The reason is the line is a lossless line. It doesn't have any resistance or inductance. So based on the load which is connected at the receiving end of the lossless line, the same quantum would flow from the sending end because there is no additional loss in the line at all. So at every point in the line, the real power quantum would be same as the real power which is being absorbed by the corresponding load at the receiving end. The reactive power, however, may be drastically different, and it significantly depends on what are the voltage magnitudes. In fact, the point that I was trying to make moments ago, that reactive power flow has lot to do with the reactive power expressions. The importance of that could be seen from these terms here. The reactive power expressions, they are strongly dominating the reactive power flows in the transmission line. And value of delta, if we were to say, the value of delta, I mean, it doesn't usually vary in a large range, even for transmission lines. Typical deltas which usually one observes or sees, which is basically, so what is delta? Let me define that first. Delta is the phase angle difference between sending end and the receiving end voltage phasor. For a well-behaved typical operating transmission line, delta doesn't go beyond 30, 40, at max 50 degrees. And if we take the variation of cosine of delta between 0 to 30, 40 degrees, the cosine value doesn't change drastically, whereas the same could not be said about sine. The sine component almost has a linear variation towards points around 0 degrees for delta. So cosine of delta being little passive in the sense that it doesn't have much variation. It often tends to be close to 1 or 0.999 or 0.98 or 0.7 at best, depending on what the delta value could be, which is not very drastically different. That's the reason why reactive power flows have more to do with the magnitudes, voltage magnitudes. And that's the reason why reactive power strongly depends on the voltage profile. It has strong correlation with voltage profile. And in order to maintain this voltage profile, as I mentioned, to minimize the real power losses, the corresponding compensation becomes necessary. So for three-phase longless transmission line loaded at surge impedance loading, there is no net reactive power flow into or out of the line. The load is perfectly resistive. Sending end power is active power with net zero reactive power input, because the reactive power output is also zero. The receiving end power is perfectly real power because the load is purely resistive. And the voltage magnitude at every point in the line is same. The profile is perfectly flat. If you recollect our previous lecture, where we were trying to see the profile of the voltage from sending to receiving end, the line was perfectly flat when the line was loaded at sending SIL. So basically, this is the line length, and this here is the voltage magnitude at different points. For SIL, the profile was perfectly same, it was uniform. For loads less than surge impedance loading, the receiving end voltage tends to be more than the sending end voltage, which is essentially the Ferranti effect, because the line charging current is being drawn, more reactive power is being generated by line capacitance, lesser of it is being absorbed by line inductance. So in order to bring down this receiving end voltage, we would require some device which can absorb this excess of reactive power. So often we use shunt reactor at the receiving end to absorb the excess reactive power, so that the high voltage magnitude at receiving end is brought down to acceptable level. Usually shunt reactors are used to limit over voltages for lightly loaded EHV lines for lines length more than 200 kilometers. Often this situation is very rare. What one would observe usually is the use of shunt capacitors for long transmission lines. So for a lossless long line, we will see a specific case where we understand how do we find the value of shunt capacitor or shunt inductor in order to properly maintain our voltage profile or smoothen out the voltage profile. So for a lossless long line, we have seen these expressions earlier. Please go back to the previous slides where you can find reference of these equations. And what we are considering is that the line is open circuited. That means there is no load at the receiving end, and we are trying to replicate the Ferranti effect into place, where the receiving end voltage would be more than the sending end voltage. And in order to bring down this receiving end voltage, we are trying to connect a shunt reactor whose value needs to be determined so that the voltage profile becomes uniform. So let's see what happens. So basically, we're trying to emulate the Ferranti effect into condition, and since we have only a shunt reactor at the receiving end, so by KVL, if you remember, by KVL we would have VR into IR is equal to JXLSH. Essentially, the receiving end voltage or the receiving end current, IR and VR, these have been connected with a reactor which is JXLH, and by KVL we have this expression which is the reorientation expression over here, and if we substitute IR in the expression here, we get Vs and Vr, where the term present inside over here is a perfect real number. It's a scalar quantity. It has no imaginary number. So essentially, Vs and Vr, they are in perfect phase. And the reason for this perfect phase happening is it's a lossless line. There is no need of real power at the receiving end. So there is no need of real power flow in the lossless line. Remember, for lossless line, PS and PR, they were equal to VR, Vs sine delta by B. Since the load is purely inductor, which is there to minimize the effect of Ferranti effect, the real power flow need not be there. Delta is perfectly zero, which is essentially indicated by this expression here. There is no need of real power flow in the lossless transmission line. This is only about the phase angle difference. We still don't know what would be the magnitudes of Vs and Vr. So if we rearrange the terms in this equation here, we can get the expression of XLS in terms of Vs, Vr, beta, LL, ZC. They are known for a given transmission line. What is unknown is the only ratio present over here. If we have to maintain the voltage profile, we would usually expect the receiving end voltage to be of some percentage of sending end voltage. So we'll come to that part a little late. We can also look at the expression of current. From the current perspective, if we substitute this expression IR over here, put VR in terms of IR into JXLH, then we have a similar expression where IS is in phase with IR, because Vs by Vr, the magnitudes could be different. Vs and Vr, they don't have any phase difference because there is no need of any real power flow. So essentially, this number also is a pure real number. The phase angle difference between sending end current and receiving end current, they are the same. There is no phase difference at all. If we want the same voltage at the receiving end with respect to sending end, essentially we would expect Vs by Vr to be equal to 1. Then for equal to 1, XLH, the ratio becomes 1, so we get this expression. And for sending end and receiving end, we see that this entire term becomes equal to -1, which is essentially why IS is equal to -IR. So essentially, that's where the little difference or aspect comes in. We remember or recollect our two-port network long lossless line where we have sending end voltage and current, we have receiving end voltage and current, and here we have our ABCD parameters. For lossless line which is connected at the receiving end by this reactor XLH, the receiving end current is negative of IS. That means actually this current which is flowing at receiving end is in a reverse direction as per the chosen notation. The same and reverse current is flowing inward into the two-port network. So one would wonder or assume that if these two currents at the sending end also we have IS, at the receiving end also we have IS, then there might come a point somewhere in the line where by KCL, since the line is perfectly represented as ABCD parameters, where we can represent it by the corresponding pi model or the T model, there might come a point which is usually going to be midway between sending and receiving end, where by KCL, the net current at this point would be perfectly zero. Just keep that thing in mind. We'll come back to this particular aspect in a moment, and why it happens, we'll also understand that. So specifically for voltage profile to be maintained uniform across the sending and receiving end, not at all points in the line, the corresponding shunt reactor should be of this value, and under this condition, the receiving end current is reverse of the sending end current. So if we now look at what is happening at midpoint of the line, where we are trying to find the value of V and I at x is equal to LL by 2, and since we know that VR and IR, they can be defined in terms of the shunt capacitor which is present at the receiving end to minimize the Ferranti effect. So what we see here is that at a length equal to x is equal to LL by 2, the voltage is simply VR by cos of beta LL by 2. Now, how do we get this expression? So, please bear with me for a moment. What we do here is we substitute IR as VR by JXLH. So, I'll work it out over a bit here. So, we have the first term as cos of beta LL by 2, which is beta LL by 2, the term present over here. Then after substitution, we have ZC by XLSH. J and J, they get cancelled each other, they cancel each other, and then we have sine beta LL by 2. The entire term has a common term of VR, which I am going to sort of ignore for time being, and I'll put it back again when the time comes in. In this expression, we put XLS in terms of this substitution. So we get cos of beta LL by 2 plus sine beta LL by 2 divided by sine of beta LL multiplied by the XLS term gets over here. So we have 1 minus cos of beta LL over here. I hope I am correct. I think it is yes. Okay. So if we work it out a bit, we have cos of beta LL by 2 plus 1 minus cos of beta LL divided by 2 cos of beta LL by 2. How do I write this? Remember, sine theta is nothing but 2 sine theta by 2 into cos theta by 2. So if I put theta as beta LL, then I have sine beta LL by 2 on the numerator, which gets nullified with the sine term on the below. So I have 2 cos beta LL. This can further be simplified as 2 cos square beta LL by 2 plus 1 minus cos of beta LL divided by the entire 2 cos beta LL by 2. So if I use my trigonometric expressions and go back and recheck, this term essentially becomes equal to 2. 2 and 2 gets cancelled. So I have 1 by cos of beta LL by 2 as the only term. Remember, VR was present. So into VR, I get Vx as VR by cos beta LL by 2. Similarly, if I work out the current at the midpoint, the current turns out to be 0. And since cosine of beta LL by 2 would be a number less than 1, it would mean that the maximum voltage would appear at the midpoint of the line. At any value of x different from the midpoint of the line, the voltage profile would be different or lesser than the receiving end voltage. So what has happened is now that we had Ferranti effect happening at the receiving end, where the receiving end voltage was more than the sending end. By connecting a shunt inductor at the receiving end, we are trying to make its voltage same as the sending end voltage. But while trying to do so, we have unintentionally popped up or amplified the voltage at the receiving end, because the shunt reactor or inductor being present at the receiving end, it was able to consume excess reactive power only at the receiving end. The line parameters are distributed. Line capacitance is generating more reactive power than the line inductance. So more reactive power has now accumulated at the receiving end and at the midpoint of the line, and hence the voltage profile has gone up there. So by compensation, we can maintain the receiving and sending end voltages, but then there could be other drawbacks or demerits of it. That's the overall intent or discussion or the summary behind this discussion. For loads more than the surge impedance loading, the receiving end voltage would be less than the sending end voltage. So reactive power will be more absorbed by line inductance, rest of it would be generated by the line capacitance. So we would need shunt capacitors or series capacitors, or for that matter, static var compensators, or we have also seen about synchronous condensers, which are actually synchronous motors operating at no load at the receiving end of the line, so that according to the need of reactive power at the receiving end, the voltage or the receiving end can be boosted up or can be brought down depending on the requirement. This increases the magnitude of the receiving end and can also help in increasing the power transfer capability and improve system stability, which we will see in the last module of stability analysis. Shunt capacitors are used to supply reactive power at the receiving end and boost local voltages. They can be either permanently connected or they can be connected through banks of capacitors, and depending on the requirement, a few of these capacitors could be turned on or turned off depending on the requirement of what the reactive power need is at the receiving end. The issue with these shunt devices, be it for inductor or be it for capacitor, is that the corresponding reactive power compensation which is needed, it could be reactive power generated or delivered, it essentially is proportional to the magnitudes, the square of the voltage magnitude at the point where these devices are being connected. So essentially, if we have a situation where the line is heavily loaded and the corresponding receiving end voltage is already lower, we expect that by connecting a shunt capacitor, the reactive power at the receiving end would go up. But then the same reactive power is proportional to the lower voltage square which is present in the receiving end, which would mean that the reactive power is proportional to square of voltage. When there is an excess need of reactive power, when the load voltage is exceptionally poor, this device itself would not be able to deliver sufficient amount of reactive power because its own deliverance depends on the square of voltage at the receiving end, which already is poor. So that's one of the demerits or disadvantages of having shunt capacitors or shunt inductors for that matter. So at the time when the reactive power requirement is the maximum, the devices are not able to generate or consume relevant amount of reactive power. So in order to get away or get rid of these disadvantages with fixed or non-switchable devices, where comes the concept of static var compensators, which essentially consists of various controllable inductors and capacitors. The inductors, they are called as TCRs. TCR stands for thyristor controlled reactor. Reactor is also alternative name for inductor, and TSC means thyristor controlled capacitors, in short TSC. Thyristors are IGBT based electronic switches which can be turned on and turned off as per the requirement depending on the gate pulse which is provided. And based on the need of the reactive power requirement, appropriate switching can or pulse signals can be given to these different switches or these I would say thyristors, which are IGBT based switches, and accordingly the relevant number of reactors or capacitors can be turned on and turned off. Static part here refers to the fact that there are no rotating parts involved, unlike synchronous condensers. And ideally, a static VAR compensator should be able to hold the voltage of the terminal at the HV bus to its constant profile, irrespective of whether the reactive power is higher or lower. Practically, since these devices are all reactors or capacitors, the profile or the ideal profile which should be expected from SVC, that no matter what the reactive current is, whether it is a capacitive current or inductive current, the voltage profile should always be a flat line. That doesn't happen in practice. In fact, practically the flat line which actually should be this perfect constant line, irrespective of whatever is the inductive current or the capacitive current. Basically, the right hand side part essentially means to the lagging power factor mode, and the right hand side part means to the leading power factor mode, and that's the reason why current here is tending to correspondingly lead the voltage, and for lagging mode in the inductive mode it is correspondingly lagging the corresponding terminal voltage. Actually, the ideal SVC should have a flat line profile, but since these are practical devices, every reactor capacitor would have maximum current handling capacity, maximum voltage bearing capacity, and hence maximum power which these devices can deliver. So that's the reason why on the capacitive side you would see a linear profile, where linear profile goes up to the point where what is the maximum voltage of the capacitor can withstand. Beyond that, the capacitor would blow off, and between these points you have a linear relationship, because essentially any straight line on VI plane would refer to the slope. So basically the slope of this line on VI plane, this slope would always refer to the impedance. In this case, the impedance that we are referring to is the impedance of the capacitor basically, and hence it's a straight line. Similarly, for the inductive part, once the capacitor has fully discharged itself, voltage has gone up, the inductors might come into picture, the dotted line might also indicate those devices. So beyond a particular portion, the corresponding slope here refers to the inductive impedance. This here could also be the impedance. The slopes might be different because the reactive value and the capacitive value, they may be different here. So that's the reason why we have linear portions and flat line straight portions for practical SVCs. We can also have capacitors placed in series. What would happen is that the overall reactive part or the overall X of the line would go down, which might turn out to be good enough because the overall power transfer capability of the line would go up, because the effective line reactance has gone down. Remember, so where is this notion coming from? This notion is coming from the fact that if we recollect the power expression for generators, similarly we have seen the numbers for or expressions for the lossless line. The real power expression here was basically a function of two voltages, V, E sine delta by X. If the value of X goes down, the corresponding value of P would go up. That's the reason why if we connect series capacitors, the overall line reactance might go down, which may help in improving the real power transfer capability of the line. But there are issues with such arrangements. Series capacitors, they need specific protection devices against line faults, and they also bring in another mechanical issue, which is known as the resonance. Because of series capacitance present, which may resonate with the corresponding inductive parts of rotating machines, the transmission line itself, the transformer itself, at frequencies or system frequency, subsynchronous resonance may happen, which might lead to permanent damage of the rotating parts, specifically the turbines. So that's the reason why series capacitors are usually not entertained or connected in transmission networks. One is the cost involved in maintaining them is higher. The other is the subsynchronous resonance phenomena, which can be detrimental to the entire transmission network, the transmission system, because series inductances of machines, transformers, they may resonate with the corresponding series capacitor during certain disturbances where the frequency might be the system frequency. So in general, the contemporary parts of how these compensations happen, this in itself is a very fascinating subject, and those of you who are really interested, I would recommend them to please refer relevant textbooks or notes where you would find details of facts, which in a way short is known as flexible AC transmission systems, where you would find details of SVRs, SVCs, STATCOMs, synchronous condensers, etc., and all those details of how do they work, UPFCs, etc. There are a lot of research which is going on. There is a lot of work which has already been done. Powertronic based devices, they are coming up, which in a way help in regulating when a capacitor should be on, where it should be on, how real power flow can be regulated, and all those topics, all those compensation aspects, they come into this domain of fact devices, which again is a very large topic in itself. We'll conclude this discussion with an example wherein we have a lossless long line, 300 kilometer long, 60 Hz is the frequency, the rated voltage is 500 kV, per phase line inductance and capacitance are given, and we have to find different aspects of the corresponding line. First is find the corresponding phase constant, surge impedance, velocity of propagation and wavelength. Then the next is finding the sending end quantities when receiving end power and load are given. Voltage is also given. Finding the receiving end voltage when the line is at no load with sending end energized at 500 kV. And finally, for bit D, we want to find the reactance which, if installed in respect to part C, would bring down the receiving end voltage, basically minimize the Ferranti effect, bring down the receiving end voltage to same voltage at sending end. So for bit A, it's pretty straightforward. Lossless long line, we have seen the expressions of beta, ZC at length, and value of U, if you observe, it is very close to 3 × 10⁸ meter per second, which is the absolute speed of light in vacuum. And wavelength is in order of few thousands of kilometers. Our country diversity itself is less than this typical wavelength. If we measure the distance from north to south or east to west, the overall entire transmission line need not have this particular wavelength. In fact, the line lengths are much smaller than the actual physical wavelengths. For part B, the receiving end voltages are given, so we choose that as a reference. Receiving end power is given, so we convert that into per phase power. We find the corresponding receiving end current, which is SR conjugate by VR conjugate. Beta value is defined, which is 0.001259 radian per kilometer. We multiply it with 300, which is the line length. We get 0.337 radian, which when converted to degrees, how do I convert this into degrees? I multiply this by 180 degrees by pi radians, and that's how I would get this number. If our calculators are set in radian mode, then I would recommend choosing this number to find the corresponding ABCD parameters given below. If the calculators are set in degree mode, please convert this into degree mode first and then use these numbers to find the corresponding ABCD parameters. So having evaluated those ABCD parameters with proper setting, we can then put in those numbers of A, B, VR, IR into sending and receiving and sending and voltage and sending and current, find those quantities, multiply them and find the corresponding complex power. Note that real part of this number and the real part of this number, which is 800 by 3 megawatt, they would exactly match each other because the lossless line is existing. So basically the line is a lossless line. There is no entity in the line which is consuming any I square R loss. There is no active power loss in the line. So whatever is the 800 megawatt requirement at the receiving end, the same quantum is supplied at the sending end with no incremental part. That means if 800 megawatt is the requirement at receiving end, the exact 800 megawatt is coming from sending end. So please verify that by taking the real part of this number, it should match 800 megawatt. Coming to part C, The receiving end voltage we have to find when the receiving end is open circuit, it is a no load. Sending end voltage is reference, so sending end we convert to the phase voltage, receiving end current is 0, so you find the receiving end no load voltage, which obviously is more than the sending end voltage, which is essentially the Ferranti effect. And in order to minimize this Ferranti effect, we now try to find a shunt reactor which needs to be connected, and we have seen this in slide 9 that XLS has this formula. So if we put Vs by Vr equal to 1, which is the one sitting over here, we get this as our number, and the rating of this particular shunt reactor in terms of reactive power device is proportional to the voltage square. Voltage is at 500 kV, so we correspondingly find the corresponding reactive power rating. That's all for this particular module. Next lecture, week 7, lecture 2, we will start with a new module, new interesting module, which is power flow analysis, and essentially there we would understand that why do we have to learn power flow analysis when so far in our second year or first year courses, or even in the preliminary third year courses, you would have understood and analyzed or talked about KCL, KVL, Thevenin theorem, superposition theorem, etc., etc. You have made use of those theorems, nodal analysis, mesh analysis. You have made use of all those to solve for circuits whose specifications are in terms of voltages and currents. So what is there new that is involved in power flow? Why do we first of all need to know power flow? Because if by using KCL, KVL, Thevenin theorem, Norton theorem, mesh analysis, nodal analysis, if we can still find the currents, voltages in short circuits, in smaller circuits, basically not short circuits, in smaller circuits whose circuit lengths could be comparable to transmission line lengths, and on one end of the transmission line you have a voltage represented by a voltage source, and the receiving end is connected by impedance. So you can still make use of KCL, KVL to find those quantities. In fact, so far for the analysis, for the model analysis, we have been using KCL, KVL so far. We have not used anything else at all. So why is this power flow analysis necessary? We will understand that by revisiting the basic circuit analysis topic, and what makes the difference of why circuit analysis cannot be used for actual networks, and which is where we would need power flow analysis. That we will discuss in the next lecture. Thank you.